Okay, as you may remember, we started seeing the properties of the Laplace transform, and the last property that we saw was the differentiation property. The time domain differentiation was something familiar to us. We may remember that from differential equations already. A time derivative of the signal will have a Laplace transform corresponding to s times the Laplace transform, x of s. And the region of convergence normally doesn't change except for a cancellation of a pole at s is equal to 0 because we are multiplying by s. This is a little bit different from the differential equations Laplace parameter, unfortunately, because over there we had the initial condition property. The initial condition is necessary for a different version or a variation of the Laplace transform. We will briefly see that as well. But this one is even simpler, as you see. It doesn't depend on any initial condition or anything. Because of the definition of the Laplace transform or the Fourier transform, which starts from minus infinity and goes to plus infinity, whereas in differential equations we use it in another form which starts at 0 and goes to infinity. Because of that, all the negative times should be handled with an initial condition. That is a difference. We will mention about that briefly. But since we are more familiar with the time domain, the Laplace domain derivative corresponding to minus t times x of t, how can we use that? Let's see an example about its utilization. This second property of the differentiation gives us a tool of managing Laplace transforms of signals which have a t multiplying a different signal. Suppose that x of t is something whose Fourier Laplace transform we already know. And if it is multiplied by t, then how can we manage the Laplace transform of that? This property helps us doing or solving that. And the example is quite trivial in that respect. It's like this. X of t is given as t times e to the minus at u of t. And as you see, the solution is quite obvious because e to the minus at u of t is a very simple signal whose Laplace transform we already know. And what is that? E to the minus at u of t has a Laplace transform of 1 over s plus a. With a region of convergence, let's also indicate that real part of s is greater than minus a because the signal is right-hand sided. It's a causal signal. Now what shall we do? We will just say that then t times that thing, e to the minus at u of t, will have a Laplace transform which is equal to minus the derivative, s derivative of 1 over s plus a. And that is equal to 1 over s plus a square, strangely. And that minus sign takes care of another negation. Therefore, eventually we have something positive. In fact, the multiplication of a first order system, which is a single exponential times u of t, the multiplication of that with a t produces 1 over s plus a square, and it truly goes on like that. The more we multiply with t, the more exponents we take. And the formula about multiple differentiation in the Laplace domain is it helps us to formulate a generalization of this phenomenon. This is only one multiplication with a single t, but if you iteratively multiply like this, unfortunately you need to normalize it with n minus 1 factorial, the power factorial in the denominator, e to the minus at u of t, it will have a Laplace transform equals 1 over s plus a to the power n. So if you multiply with 1t, it will be 1 over s plus a squared. If you multiply it with t squared and divide by the factorial of 2, which is also 2, then you will have 1 over s plus a cube. And it always goes on like this. The formulation can be generalized like this. It's just an observation, and it doesn't really require a lot of proof, because the derivative will automatically help us doing that. And the factorial also comes from iterative differentiation. There's a power, and when you differentiate it, it will have it's multiplied, and then the power will be reduced, and then it will come back. So the scale will be n times n minus 1 times n minus 2 times, etc., which corresponds to n factorial. That's where the factorial business comes into the picture. So this is perhaps the single most important observation that we can utilize, where we can utilize this property. Another property, now I will continue, is an integration. And integration, by integration I mean this. From minus infinity to t, we have our signal integrated. And the Laplace transform of this one is fortunately much easier in terms of the representation than the Fourier transform. It's quite simply 1 over s times x of s. And the region of convergence is equal to the previous region of convergence, or let's not say equal to, let's say it includes, because there may be again pole zero cancellations. It includes the previous region of convergence of x of s intersection with a new region of convergence telling us that real part of s must be greater than 0, because we are now adding a pole at s is equal to 0 with 1 over s. And consequently, it imposes a new region of convergence. Real part of s is greater than 0. We must intersect that with the previous r. And if there is a pole zero cancellation or anything, it may be more than that, but at least it is the intersection. By the way, in the system block diagram chapter, if you may remember, one of the first chapters that we have seen in linear and time invariant systems, do you remember that we were drawing our system blocks using an integrator, not using a derivative function? The discrete versions were with a d, which means a delay, but the continuous versions were with an integral. You remember that? Now you would agree that instead of the integral, it's more systematic to use the same blocks, but indicate them with a 1 over s in the Laplace domain. So in the book, you will see that those blocks may be automatically translated into a 1 over s with the same ideas, with exactly the same ideas. Probably we will see a few examples about that one as well. But you may remember that 1 over s comes from this phenomenon. This is not a property but a consequence of the Laplace transform, which relates the limit values of the signal. The limit value says that it says two things. The time signal at 0, but I will say 0 plus. That is, in case of discontinuity, the discontinuous part must approach from the right hand side. It means 0 plus is equal to s times x of s as s goes to infinity. Where does it come from? Why is that the case? The proofs of these limits, this is the first limit that we will have, are quite fascinating. Because by multiplying with an s, you essentially take something like the derivative, don't you? It's like you take the derivative. And then what does it mean as you take s to go to infinity? What does that mean? What kind of an area it corresponds to? I would really like you to think about that. Just try to think about these limits, why they are essentially giving us the value of the time signal. Later on, you will find the answers in the book. They are there. I mean, the explanations are briefly there. But thinking about these will help you better understand the Laplace space and what's going on the Laplace space. The second one is the value of x of t as time goes to, as t goes to infinity is equal to, as s goes to 0, s times x of s. Now what does that mean? Okay, these are interesting phenomena that we will see. Do you remember the number of poles and zeros and things like that as t goes to infinity if they approach to something 0 or infinity or a single value? How we were thinking of those with the number of poles and zeros. How does this help? I would really like to think about. I would really like you to think about that. If you're having difficulties from the explanations of the book, please come and consult me. But before that, I want you to literally think about that. Unfortunately, the limit values, they don't help us solve problems other than the problems themselves. I may give you the x of s polynomial over polynomial thing. I can give you that. And I can ask you what is x of 0. Then all you need to do is just multiply the polynomial ratio with an s and take s goes to infinity and what is the value of that. It will either be infinity or a finite value or 0. If the denominator is stronger, it will be 0. If the numerator is stronger, then it will go to infinity, the powers I mean. If they are equivalent after the multiplication with an s, if they become equal, then the limit is just the highest polynomial power term in the numerator divided by that term in the denominator. For example, if it happens to be from here, if it happens to be a times s to the n plus something which are lower than s to the n, like s to the n minus 1, s to the n minus 2, etc., divided by b times s to the n plus lower terms, then the limit is a over b simply, as s goes to infinity. Do you understand what I mean from here? So the solutions will be like that. If the numerator or the denominator powers, maximum powers are different, then it will be either 0 or infinity in the limit. Otherwise, it will be a over b like this. Okay, so these are the properties that we will see, or we will cover briefly. With these properties, we have to solve questions and we have to design systems. Of course, there is a table with that, with these properties. I believe that you must have already brought them to the second midterm, just in case I could have asked a question, which I didn't. I mean, I asked a relatively simple question because we didn't cover a lot of Laplace transform before the second midterm. For the time being, we have covered everything, so that table will be more useful to you in the final examination. Okay, now let's start some examples. What sort of questions can we solve with these? What could be asked? It could be, for example, like this. X of t goes into a linear and time invariant system which I don't need to indicate to be linear and time invariant anymore. If I write the impulse response with h of t, it automatically means that it's an LTI system, and therefore we have the Laplace transform as well. And the output is y of t, where x of t and y of t black box experiments are carried out. The first black box experiment that we did was applying an impulse and observing the response, which was h of t, impulse response. The first black box experiment. But now, since we know other tools like Fourier and Laplace, then we can enrich our black box experiments. For example, if I apply this input and make an observation at the output to be equal to e to the minus t minus e to the minus 2t u of t, what can we say about the impulse response? This black box experiment, by the way, is much more manageable as compared to applying an impulse and observing the impulse response. The reason is you cannot apply an impulse. It doesn't exist. It's not physical. You cannot experiment with that. This one, yeah, you can do that. The function generator, you may just apply this e to the minus 3t u of t, a decaying exponential abruptly starting at some point, and you record the output and model it. The model, let's assume to be like this. So what is the impulse response? The impulse response is perhaps the farthest that you can think of. We already know how to solve these questions using the Fourier transform. You remember that? You could take the Fourier transform of the input and the output and divide them from that ratio, y of omega divided by x of omega, will give you h of omega. You could do it that way. But now we can also solve it from the Laplace transform. X of s is equal to 1 over s plus 3. It's even simpler to write, as you see, with a region of convergence, real part of s greater than minus 3. And this one will have y of capital Y of s to be equal to 1 over s plus 1, s plus 2. I'm skipping some details here, so don't get confused about the fact that how did I write that. Normally I should be writing like 1 over s plus 1 minus 1 over s plus 2, because we have two components over there. Their summation is this one, okay? It's a little bit simplified. So you cannot just simply write it this way if the parameters are different. Be careful, I'm skipping some details over there. But eventually this is what you get. And the region of convergence is real part of S is greater than minus 1, which is the rightmost pole among the two poles that are minus 1 and minus 2. Since it is right-hand sided, we have to choose the rightmost pole. And when we write h of s to be equal to y of s divided by x of s, and this comes from the multiplication, convolution in time versus multiplication in Laplace domain property. It will be s plus 3 divided by s plus 1, s plus 2, with the region of convergence. Immediately from this expression, there are two poles at minus 1 and minus 2, and we have to choose the right-hand sided version because the input-output relation is right-hand sided input versus right-hand sided output. Therefore, the real part of S should be greater than the rightmost pole, that is minus 1. Although I asked you to find the impulse response, it may be a little bit problematic. You may think of it as an exercise for you, because as you see, I don't solve the exam questions before asking. So they may be a little bit overly difficult sometimes. I don't know whether this one is overly difficult or not, but how would you find the inverse Laplace transform of this expression? That would give you h of t. How would you do that? just split it into two terms, a over s plus 1 plus b over s plus 2. And find a and b, which yields the numerator to be equal to s plus 3. You will have two equations with two unknowns. Two unknowns are a and b. Two equations are something of a and b will be equal to the coefficient of s, which is 1. Another combination of a and b will be equal to 3. Like this. You will have to come up with those. And then you may find the inverse Laplace transforms of two first-order systems. Okay? So that's how you find the inverse Laplace transform, which I don't know. I mean, I haven't done it yet. But another alternative question that may be generated from this question is, what is the input-output differential equation? That is another way of looking at the differential equation or the system. That is like this: y of s over x of s is equal to s plus 3 divided by s squared plus 3s plus 2. Right? You can write it like this and make the cross multiplications and say that y of s in parentheses s squared plus 3s plus 2 is equal to x of s in parentheses s plus 3. And then the inverse operation of that into time domain is quite trivial. A multiplication with an s will correspond to a derivative. A multiplication with an s square means twice the time derivative. So you can easily write it like this: d square over dt square y of t, which comes from this s square term, plus 3d by dt y of t plus 2y of t is equal to d by dt x of t plus 3x of t. Right? As simple as that. So this is an example about solving system questions from input-output to a differential equation or to an impulse response. Okay. It could be anywhere. It could start with any of these three and end with any of the other three. Very well. Now, I want to continue with, although I'm writing it as an example, it's like incorporation of a subsection into an example, and that is the system diagrams that I have mentioned like minutes ago. Now, how can we draw the system block diagrams of some input-output relations in the Laplace domain if the system is given in the Laplace domain? So the example is as follows. H of s is given as 1 over s plus 3. The question may start from here, 1 over s plus 3, or it may start from an impulse response or an input-output relation, and you come up with this. From here on, now we have another subsection of the question. Part A, find this. Part B, find the Laplace transform. Part C, find the impulse response, whatever. And now part D, I'm asking you to draw it in the block diagrams, using the block diagrams. And the block diagrams must use either scales and coefficients, which mean attenuation or amplification, whatever, or 1 over s components. 1 over s components are integrators that we were using in the first chapter. Now you continue with the block diagrams like this. You write it in this form, not h of s, but y of s over x of s, and then from here you write it like this: sy of s plus 3y of s is equal to x of s. Now, no matter how higher an order it may have, this is a first order system, sorry. It's a first order system, which means that the maximum S polynomial coefficient, which multiplies y of s, is equal to s. It could be s squared, s cubed, whatever, for higher order systems. This coefficient of y of s, the highest s polynomial coefficient, determines the order of the system, and this is a first order system. What you need to do is you must isolate the highest order y of s component at one side, at the left hand side, in other words. Let's do that. And for this case it is s times y of s, so let's isolate it and put everything else to the right hand side. So I'm gonna write it like okay, x of s minus 3y of s, isn't it? It's like this. I'm keeping the highest order at the left hand side, and then I divide it by the s polynomial order to isolate and make it individual y of s at the left hand side. So y of s is equal to, then it will become like this, 1 over s times x of s minus 3 over s, or 3 times 1 over s, y of s. It happens to be like this now. And as you see, it is much easier than trying to solve it using, or trying to convert the time domain differential equation into an integral equation. Now what I did is quite simply convert the top differential equation, that is a differential equation, into an integral equation. The top one was in terms of s coefficients, multiplying here and there, or s square, s cube, whatever. Now I'm converting everything into 1 over s square, 1 over s cube type of structure. That is the link from the differential equation into an integral equation. In time domain it was much more difficult to understand. Now it's easy. And 1 over s that we see here is nothing but an integrator. So what is the implementation? The implementation is quite simple. You say you have an x of s. I'm writing in the s domain, but the time domain overall implementation will be the same. Instead of 1 over s, you just need to put an integral symbol. And at the output we have a y of s. This is the input-output relation. Now what's happening to x of s and y of s to form and recombine into y of s itself? First of all, there is a nice trick showing us that y of s is multiplied by minus 3 here and added to x of s, and the whole thing is multiplied by 1 over s. So what I'm doing is something like this actually. In 1 over s parentheses we have x of s minus 3y of s. Okay. Therefore, in the lower branch, I'm saying minus 3 times y of s, and from here x of s comes in, and they are added, combined. In a parenthesis, everything is multiplied by 1 over s. So this 1 over s thing here is nothing but an integrator. Okay. This is the implementation of a first order system. If the order of the input, okay, let's look at the input-output relation in the differential equation, the first differential equation. If the order of the output s is greater than the order of the input, then we will always have integrators. But remember that you will have to isolate the highest order output parameter y of s and divide all the system by its power. If it is s, divide everything by s. If you have an s square here, for example, which multiplies x of s, although you divide by s, it will still be s times x of s, for example. The input or the upper branch here may have differentiators as well. I told you that you must use integrators, but if the order of the input is more than the order of the output, then there may still be some differentiators, derivative components. Instead of 1 over s, you may still have s. What do I mean about that? Let's see an example. This time h of s is given as s plus 2 over s plus 3. Okay. Now here, my recommendation is that the polynomial side, just forget about it. Keep it as it is. Don't worry about that. It's the denominator part that I'm asking you. So it's not like the solution of the time domain block diagrams where we were trying to combine some of the integrators to save from the number of integrators, to minimize the number of integrators. For the time being, just forget about that and try to solve it like this. Say that this one is equal to 1 over s plus 3 times a whole new system s plus 2. So just solve 1 over s plus 3 and then cascade it to an arbitrary or a very simple system saying that the rest is s plus 2. 1 over s plus 3, we already know the answer. What was that? So x of s is the input. Just the top shape over there I'm drawing again because it's the same answer. Minus 3, you multiply and feed it back like this. This is 1 over s plus 3. We all agree with that. And I'm now cheating by saying that the rest of the system is s plus 2 only because it's in the numerator. Its implementation, I don't even care. So you can do it like this. And this will be a valid answer. As you see, it's much simpler than what we did in time domain, basically. You have to focus to the denominator portion, 1 over s plus 3. The numerator, you just leave it as it is. Now, let's continue with another example, which is second order. H of s is equal to 1 over s plus 1, s plus 2, which is equal to 1 over s squared plus 3s plus 2, which is also equal to 1 over s plus 1 minus 1 over s plus 2. Now I'm writing separately, individually, one by one. This version, and that version. Because those three versions will enable us to draw the block diagrams in three alternative ways. You can draw it in three ways. Let's look at the last one. 1 over s plus 1 minus 1 over s plus 2. Perhaps it's the easiest to start from that. Let's call it 1. How do we draw 1? 1 over s plus 1 starts with an input. So x of s is here. And its output is here with a feedback of minus 1. Like this. Do you agree? This is 1 over s plus 1. Now, I'm going to draw 1 over s plus 2, the second term. Therefore, we have a minus 2 here. This is 1 over s plus 2. And what I need to do is, I need to take this one and this one and subtract the second one. And the output is y of s. Are you happy with it? I just implemented in a parallel way, in other words. It's a parallel implementation of two first-order systems. The top one and the bottom one are parallel going. And the second one had a minus sign. 1 over s plus 1 minus 1 over s plus 2. Therefore, the second branch is just subtracted because of that minus sign. It's a linear summation, in other words. Yeah. Because that's what it is. I mean, if you just combine that, you will find this one or that one. They are equivalent things. What is s plus 1 minus, in parentheses, s plus 1? Remember that if you try to combine this, come on, it will be, this one will be multiplied by s plus 2, this one will be multiplied by s plus 1, right? So s plus 2 times 1 is s plus 2 minus s plus 1 with the inner parentheses will give you 1. It will be, this will be exactly equal to this one, and that is naturally equal to this one. I know the answer already. That's how I could write the answer. Okay, I didn't try to solve it. I know the answer already. So this is the first implementation. Now let's implement it using this one. The first implementation required parallel first-order systems and combining them at the output. This second implementation, let's give it a number 2, is this time it will consist of cascaded implementations. As simple as the first one, because this thing is a multiplication of 1 over s plus 1 and 1 over s plus 2. You just multiply them. What does a multiplication in Laplace domain correspond to? If you multiply two Laplace domain things, it means the systems are cascaded after one another. Or in the time domain, you have to convolve the impulse response of this one and this one. That means a cascading operator or a series. The first implementation was a parallel implementation. Now let's try the series implementation. And that will be one over s plus 1 implementation, which is this, isn't it? And then I have to cascade it with the second implementation. With minus 2 feedback. And the input is x of s, output is y of s. Just a series combination of the two systems. Amazingly, the top one and the bottom one are equivalent. They correspond to the same systems. Now let's come to the third variation. It's neither parallel nor series implementation. It's a direct implementation. It's a second order direct implementation, and that one is it's not very much complicated, but it's not as trivial to apply like cascading or writing first order systems. But you will perhaps understand why I'm doing it this way. The input is x, and then it is integrated, and then integrated again. After the first integration, it is multiplied by minus 3y, because that's what it is in the denominator. And after the second integration, you have to multiply by minus 2, and then you have to combine the feedbacks like this, and the output will become y of s. But while doing this, you have to be a little bit careful about trying to convert the differential equation of y and x in this middle third implementation. Maybe I skipped too many details, too many steps. So let me a little bit more brief about that. Let me open a parenthesis about how I did this second order direct implementation. Y of s over x of s will be equal to 1 over s squared plus 3s plus 2, wasn't it? Yes. And from here, you can write it like s squared y of s plus 3s y of s plus 2y of s is equal to x of s. Now, do you remember the trick? You have to isolate the highest order polynomial multiplying y of s at the left hand side. So s squared y of s is here, is equal to x of s minus 3s y of s plus 2y minus 2 y of s. Do you agree with this? Now I have to divide all the terms by s squared to isolate a y of s at the left hand side, and that is y of s is equal to 1 over s squared x of s minus 3 over s y of s minus 2 over s squared y of s. Now look at this formula. That formula says that this x of s needs to be integrated twice. 1 over s and then 1 over s. Look at the top figure. The input is integrated here and integrated there towards obtaining y of s. And then y of s itself needs to be integrated twice before scaling by minus 2. So this scaling by minus 2 is fed back into here, the first summation, but that's not enough. It is also combinedly coming back to here. So that y of s at the output is multiplied by minus 2 and it comes here. When it arrives there, its value is multiplied by 1 over s and 1 over s again to form y of s, which means twice integration. That's why we have minus 2 times 1 over s squared y of s. But we have an extra term here, which is minus 3 times 1 over s. That is one less integrated version. That one less integrated version comes from here, which is one less integrated because it's coming from the previous integration. At this point, multiplied by minus 3, scaled by minus 3, and it arrives here, and then it is integrated again. That's why we have a minus 3 times 1 over s term. Unfortunately, everything doesn't fit into the shape. To combine, we have this kind of an equation. This last equation, the formation of those direct implementations are a little bit more difficult or cumbersome. It requires more attention. But once you see the idea or the relation between this second order integral equation and this second order direct implementation, just look at them. I'm sure you will be able to copy that to make it, let's say, third order or fourth order. If I just increase the length of the right hand side to higher orders, can you just associate it with a figure like this. I'm sure you will be able to do that. You just find the association. The best way to learn the direct implementation is to find this association. And by copying this item by item association, you will be able to draw the direct implementation as well. Typically, the questions regarding the implementation, system diagram implementation in Laplace type questions will require you to draw these three types, all of them. Implement it using a parallel implementation, which is the first type. And then I can say the cascade implementation, which is the second type, and then the direct implementation, which is the third type. Okay? You may be asked to do them, to do all of them, one by one. So it may be a good idea to think of third order systems, for example, as a candidate exam or an exam candidate question. Okay? Because of course I won't be asking fourth order or anything. It would be too difficult to handle a fourth order equation or anything. But third order, maybe I can ask. Okay? Just think about that. Alright, now let's give a 15 minutes break. After that, we will continue with the differential equation type Laplace transform that we have seen, and what is the difference between this one and the one that we will see.